Okay, greetings aspiring scientists. Welcome to my video today, getting into talking about gas laws. This is kind of more of a physics topic than chemistry, but it does belong in physical chemistry as well, and there are some links to balanced chemical equations and reactions that we will certainly see with gases. So it is important as well. So let's go to my slides and get started. So we're going to start with 1.4.6, still part of section 1.4 about moles. But I will move on to 1.5 today and sort of link these together. It's not something I would normally do, put 1.4 and 1.5 topics together in a video. But these ones basically do belong together, the end of 1.4 and the beginning of 1.5. So that's what we will be doing. So 1.4.6 is about Avogadro's law. You might remember Avogadro as the person who Avogadro's number is named after, who had a lot of the initial ideas of what a mole should be, and that there should be this number that links together the molar mass and the mass of some compound or element. Same guy. So what's going on here with Avogadro's law? I think I actually introduced this when I introduced Avogadro's number as his main contribution, but in the early 1800s, Amedeo Avogadro suggested that equal volumes of gases at equal temperature and pressure must have equal number of particles. And number of particles being directly related to moles means same number of moles as well. Should be true. So this has been demonstrated experimentally since then to basically be true, with some exceptions. The main exception is that this is only true for ideal gases, or perfect gases, gases which obey a set of rules in a set of conditions. So if we have an ideal gas, a perfect gas, then we can say gases at equal temperature and pressure must have equal number of particles, equal volumes as well. Okay. So what does this come down to mathematically? We can get several useful equations out of this. The first is the relationship between the amounts and volumes of combinations of gases at constant pressure and temperature. So we can have this N1 over V1 equals N2 over V2. This is a consequence of the statements I made on the previous slide, where volume is directly proportional to number of particles, number of moles. So you can kind of treat this as initial and final conditions, N1 and V1 being initial, N2 and V2 being final, and we're changing, volume or number of moles, one of those, N or V, in the final conditions, and that will necessarily change the other one, okay? If we change N1 to N2, V1 will go to V2 if we keep constant pressure and temperature as well. So the result of this relationship is that for gases, volumes can be used instead of moles when considering a balanced chemical equations. We can use volume ratios instead of particle or mole ratios, which is very useful and very convenient. So for example, here I have the Haber process, a famous chemical reaction. 3 moles of H2 gas plus 1 mole of N2 gas goes to 2 moles of NH3 ammonia gas. Everything is a gas here, and normally we would have to go find, the mass of these, find the molar mass of each, find out how many moles are actually used or produced. But Avogadro's law, one consequence of Avogadro's law is that we can use volume ratios instead of mole ratios. So 3 volume parts of H2 plus 1 volume part of N2 will make 2 volume parts of NH3. And it doesn't really matter what units of volume that we use as long as they're all the same. So we could use liters or decimeters cubed or meters cubed, whatever you like. But if I use, for example, 3 liters of H2 and 1 liter of N2, I'll always produce 2 liters of NH3. So you can see why that's convenient and useful, I hope. So here's a visual depiction of that. 1 part C3H8 plus 5 parts O2. We can consider this liters maybe, although it doesn't have to be. So 1 liter of C3H8 plus 5 liters of O2 will make 3 liters of CO2 gas. And then what about water? Water is not a gas in this, H2O. And so Avogadro's law does not apply, okay? But it doesn't ruin Avogadro's law for the other 3 parts, which are gases. We can apply Avogadro's law to those. It's just H2O, we don't know how much will be made because liquid volume doesn't follow Avogadro's law. It is not an ideal gas, for sure. So if you wanted to find out that, you'd have to do other methods like use mole ratios and then multiply by the molar mass to get the mass of H2O. And then if you really want the volume of H2O, you could use the density, which is generally 1 gram per milliliter. Okay, so that's a good visualization. Moving on. That's basically all that there is to this, so let's do some practice. The combustion of hydrogen sulfide proceeds as follows. 2 H2S plus 3 O2, both gases, go to H2O liquid and 2 SO2 gas. Now calculate the volumes of oxygen consumed and sulfur dioxide produced. If the volume of hydrogen sulfide combusted was 0.814 decimeters cubed, all volumes are measured under the same conditions. Okay, so that all volumes are measured under the same conditions means basically constant temperature and pressure, so we can use Avogadro's law. So what might we write here? We can look at the ratio of H2S to O2. We want to know how much oxygen is consumed here. I don't really want red. Sorry. So H2S to O2 ratio. What is that equal to? We can look at the balanced chemical equation here. It's going to be equal to 2 to 3. And according to Avogadro's law, that means the volume of O2 will be equal to 3 over 2 times the volume of H2S. Which is given in the question. 0.814 was combusted. And that will give us a number. It's about 1.22 decimeters cubed. So that's the volume of oxygen that will need to react with our H2S. There's another part to this question though, which is how much sulfur dioxide would be produced. So again, what's the ratio of H2S to that, to SO2? In the balanced chemical equation, it is 2 to 2, which is the same as 1 to 1. So that means the volume of H2S equals the volume of SO2 that would be produced. Okay, so just to make this clear, the O2 at the top, this was consumed in the reaction, or it will be consumed. But this SO2 is produced on the right side of the equation, but it's still linked to the starting materials through ratios. And so we get exactly the same amount SO2 produced as H2S was used. So very convenient. We didn't have to go to the periodic table and count up the masses of all the atoms in these and do a bunch of calculations. Okay. I think I have another practice for this. incomplete combustion of hydrogen sulfide, H2S, from the previous question, produces elemental sulfur instead of SO2. So we have a new balanced chemical equation here. 2H2S gas plus O2 goes to 2H2O liquid plus 2S solid. So we don't have any gases in the products this time. But we could still answer this question. Calculate the volume of combusted hydrogen sulfide if the volume of oxygen consumed in this reaction was 2.61 decimeters cubed. So we will just want to, again, compare these two. So what's the ratio of O2 to H2S? It's 1 to 2 in this equation. So what I would like to know is what's the volume of H2S that would consume 2.61 decimeters cubed of oxygen. So it's going to be double that volume of oxygen, which was given in the question, 2.61 decimeters cubed. So that will give us about 5.22 decimeters cubed of H2S that would react with that much oxygen. Okay, so even though we don't have any gases in the products, we can still answer questions about how the reactants and the starting materials will combine together using Avogadro's law. Okay, very useful. So that brings us to the end of section 1.4 of the IB Chemistry SL syllabus. So it's been a couple videos, but we had a guiding question at the beginning of this section. How do we quantify matter on the atomic scale? So hopefully through my videos and through any textbooks or materials you have, you could answer this now. And we use things like the idea of the mole, the atomic mass unit. We use mole ratios and balanced chemical equations. We use Avogadro's law in connection to gases. Quite a lot of things. So even though we cannot pick out or count individual atoms, we have mathematical ways to link and model the amounts of particles in there through the idea of the mole. Okay, so we'll move on to 1.5. I think this is the last section of structure 1. It's all about ideal gases, so it is directly connected to what we just did with Avogadro's law. So we have a new guiding question for this new section. How does the model of ideal gas behavior help us to predict the behavior of real gases? So I've said that a condition of using Avogadro's law is that we have an ideal gas, a perfect gas that obeys some laws. But it turns out the ideal perfect gas doesn't really exist 100%, especially if you just consider gases that are around us in everyday life. You know, our atmosphere here contains nitrogen, oxygen, CO2, and various other trace gases. None of those are perfectly ideal, but we're going to try to answer this question. If we study what an ideal gas would do, can we use any of those insights to actually have practical applications on real gases? So 1.5.1, assumptions of the ideal gas model. We'll start with this. So first, the kinetic theory of gases. This slide is hugely important. There's no real math in it. It's just the idea of how we are modeling ideal gases through descriptions. A lot of physics in this, but you do have to know, I think, each of these 5 points that I have on this slide, so memorize them. 1. Gases are composed of very small particles, which we'll consider to be spherical and symmetrical. which are far apart from each other. So there's a whole bunch of empty space in between any two particles that you would choose on average. Most of the volume in the container that they exist in is empty space. So most of an atom is empty space anyway, right? It's the dense nucleus in the center with electrons in the cloud around it. But even beyond the atoms in gases, like the space between atoms is hugely empty space. That volume is mostly empty space. Second, number two, these particles are moving in straight lines in any direction. Okay, so they're not curving or taking strange paths. They move in straight lines until they collide with something. And it's in any direction, so there's no preference for up or down or left or right or forward or backwards. Basically, they all have equal chance. If you selected any random particle, it has an equal chance to be moving in any direction. Third, these particles undergo elastic collisions. So anyone taking IB physics, somewhere near the start of the course, you'll probably learn about collisions and momentum and kinetic energy transfers. So it also applies a bit here in the kinetic theory of gases in chemistry. We have to know that an elastic collision means no energy is lost. So there's different types of collisions, but I want you to imagine like billiard balls on a pool table. When they hit each other, energy is transferred basically 100%. Either the ball bounces off and maintains its energy, or it transfers to another ball. But they will basically keep moving for quite a while. Eventually, friction and air resistance will cause them to come to a stop. But near the beginning there are elastic collisions where energy is perfectly transferred. You can also think of like a bouncy ball. If you ever had one of those when you were a kid, you drop it, it collides with the ground, and basically it will come up to the same height where you dropped it from, and you can just catch it again. That's also nearly an elastic collision. So we're going to imagine our gas particles collide with each other elastically and collide with the walls of the container elastically. So no kinetic energy is actually lost from our ideal gas through collisions. Fourth, these particles apply no force of attraction or repulsion on each other. Okay, so we will learn when we get into chemical bonding and material properties that atoms and molecules apply attractive forces most of the time on each other. And that's what, holds materials together in the real world here. But for ideal gases, we're going to assume that there is none of this. Okay, that's why they travel in straight lines. They don't curve to approach each other or be attracted to each other. They basically don't even consider each other existing until they collide with one another. Okay. Fifth, the kinetic energy of a gas is directly proportional to the temperature. This is something I mentioned when I introduced temperature. Generally, we can say this. But all 5 of these points apply to ideal gases only. So you can probably think of or find some exceptions to these rules when we look at real gases, especially things like water vapor or ammonia gases. These things do have significant attractions to each other, and they're going to mess up a lot of these points that we have on this slide. So these things are the description of an ideal gas in standard conditions. So let's move on. The first law that we're going to consider is called Boyle's law. Mainly worked on and discovered by a scientist named Boyle. So I want you guys to imagine a gas, a bunch of these little spheres in a container. This is before compression, okay? They're in this volume, initial state. So what do you think would happen to the pressure if I suddenly start to move the right side wall of this container towards the left and I decrease this volume? You can probably imagine that these particles, the number of these particles will stay the same, but they'll be crammed into a smaller volume. Okay, so kind of like this, we have more densely packed gas particles now. They're going to be colliding with each other and colliding with the walls more often, more frequently. So this is the idea of Boyle's law. Volume and pressure are inversely related, right? What we have done here is decreased the volume and the pressure inside has increased. You can kind of imagine the same thing with balloons. If you ever blown up balloons for a birthday party or something, you have a balloon. If you squeeze it from kind of all directions with your hands, the pressure inside will increase. So what can we do with this mathematically? There are some equations and graphs to know. So in the bottom right, pressure is proportional to 1 over volume. That means as volume increases, pressure decreases, and as volume decreases, pressure increases. There is a condition on this, though, in the bottom left. So this is at constant temperature and amount of gas. So we're assuming no gas particles leave or enter the container, and we're assuming the container is allowed to sort of equilibrate and remain at a constant temperature. Okay, so you would end up with these two graphs. If you just graph volume versus pressure of a gas in a container, you'll get the graph on the left. It is a hyperbola. It looks kind of like the graph of 1 over x, or y equals 1 over x, if you've studied that in math. So my units here are liters and atmospheres, but it doesn't really matter what units you choose here. You'll basically always get this shape of a hyperbola. But we don't really like working with hyperbola. There's no real well-indicated slopes or points on a hyperbola. So we would like to make this a straight line. And what we can do is graph 1 divided by the gas in the container's volume versus pressure. So I would just take basically the values on the left graph and do 1 divided by that number. Or your calculator has an x to the minus 1 button. You can use that. You'll get these new numbers. And that's 1 over volume in units of 1 over liters, or decimeters to the minus 3. If you graph this, you'll get a straight line, and it goes essentially, it would go through 0, 0. I created this through Cloud AI, which didn't have 0 on the x-axis here for pressure. Pressure is in units of atmospheres on this graph. So 1 atmosphere is basically room pressure or standard pressure. But it could be in other things like pascals or millimeters of mercury or other things. You should still get this graph of a straight line that would go through 0, 0. Constant slope. Okay, so a result of this relationship, pressure proportional to 1 over volume, or inversely proportional, is this equation on the bottom right, P1 V1 equals P2 V2. So again, we can consider 1 as initial conditions and 2 as final conditions. So if we change the volume or the pressure, the either volume or pressure, must also change accordingly. So oftentimes you'll be given 3 pieces of information that you can put into this equation, and then you can solve for the 4th unknown one. So let's see an example of that. Boyle's law. So some notes about pressure units first. So pressure has various units. Newtons per meter squared, which is a force per unit area, or joules per meters cubed, energy per unit volume. That's also a pressure. Or kilogram per meter per second squared. That's just in the SI base units, okay? All of these 3 things, the green, pink, and blue, are the same. It's just joules and newtons are not SI base units, so it changes the unit on the bottom a little bit. But in SI base units, it's kilogram per meter per second squared, which is known as pascals, PA. So PA is essentially all 3 of these things, but in SI base units, kilogram per meter per second squared. We also have something called standard pressure. STP stands for standard temperature and pressure, but we're just talking about pressure for now, so that pressure is 100.0 kilopascals. And it is kilopascals, so to get to pascals, you would have to multiply that by 1,000. So here's our practice question. A weather balloon has a volume of 6.00 decimeters cubed at ground level. The pressure at ground level is 101 kilopascals. The balloon rises 4,200 meters, where the new atmospheric pressure is 45 kilopascals. And I think we do, to answer this question, have to assume constant temperature, that the temperature at ground level and up in the sky is the same, which is highly unlikely. We will learn how to account for that later in my next video, but just for now we need to assume constant temperature, which makes this a very weak approximation. So what's the new volume then? So we're going to use Boyle's law. What we have is initial volume, V1, 6.00 decimeters cubed. This can be done with any volume, but whatever you put into this equation is what you will get out. So just be aware of that. What else do we have? We have the initial pressure, P1, 101 kilopascals. We can keep it as that. Then we have P2 after rising, new pressure, 45 kilopascals. So it is important that this P1 and P2 are in the same units for this equation to work out, because we're going to be using them kind of as a ratio. We need those units to cancel out. What's the new volume, V2? That's what we don't know. Okay. So we can use Boyle's law. I'm going to want to find V2. So I'll set this up. V2 P2 equals V1 P1. Same as the equation I wrote on the previous slide. And I'll solve this for V2 by dividing both sides by P2. And put my numbers in. 6.00 decimeter cubed, 101 kilopascals, divided by the new pressure, 45 kilopascals. So you can see these kilopascals units will cancel out. You don't have to convert them to regular pascals in this particular equation. So I'll be left with units of decimeters cubed, and I will get around 13. I can only write two significant figures. I think it's really 13.46 or something, but because of this 45 only having two significant figures, I will also only write my answer here with 2, so about 13 decimeters cubed. So does that make sense? A 6 decimeter cubed weather balloon at atmospheric pressure rises up to lower pressure and expands to nearly double the size, 13 decimeters cubed. Yes, this does make sense because the pressure has over halved, so we should over double our volume here, if they are inversely proportional, which they are. Okay, moving on. Charles' law, another scientist, another law here, and it involves different properties, this time temperature. So Charles' law says volume is directly proportional to temperature at constant pressure and amount of gas. That's a condition for this to be true. So we also have standard temperature now again, part of STP. That is 273.15 Kelvin. That should look familiar because that is exactly 0 degrees C. So anytime we see STP, we have to know it means this temperature in Kelvin. So this temperature and the pressure from the previous slide are in the data book, chemistry data book you can look at pretty much any time. So what we have here is volume is directly proportional to temperature, as long as pressure and amount of gas are constant. That will lead us to the equation on the right, V1 over T1 equals V2 over T2, where again, 1 represents initial conditions, T represents final conditions. And we'll get this graph of a straight line, directly proportional relationship that goes through 0, 0. Again, units I have liters on the left and Kelvin on the bottom. Reminder that if you didn't have Kelvin, if you had Celsius instead, this graph wouldn't quite look the same. 0 Celsius is 273 Kelvin. So the graph would basically look like it starts here at this yellow dotted line I just drew. But we are graphing this Kelvin versus volume here in liters, and we get this straight line. Okay, so volume is directly proportional to temperature. If we increase volume, if we want to have the pressure be constant, we also increase the temperature. And the opposite is true if we decrease. Alright, let's see if we have a practice question. We do. A piston chamber in an engine contains 88.5 milliliters of a gaseous fuel at 24.0 degrees C during the day. At nighttime, the temperature falls to 11.0 degrees C. The atmospheric pressure applied to the piston plunger is constant through the day and night. Okay, so if you don't have experience with pistons and engines and chambers, this might not make a whole lot of sense to you immediately. But you kind of have to be able to pick out what's happening in questions like this. So we have some kind of piston in the engine, and we have a plunger that will move up and down, changing with the volume of this gas. And we have an atmospheric pressure constantly applied to this. So that means our gas basically should be at constant pressure every time because it will just equilibrate with the pressure outside. Okay, this is in contrast to like just a glass sealed container that can't change its volume at all. This piston chamber can change its volume, and the pressure will basically be constant at atmospheric pressure. So what's the volume of the gaseous fuel at night? Well, one thing I'm going to warn you about here first is that to have Charles' law make sense, we need the temperatures to be in Kelvin. There's several reasons for this. If it was in Celsius, you could end up with things like fractions with 0 on the bottom or 0 on the top, which wouldn't make a lot of physical sense. They'd be undefined, even though you know something can cool down to 0 and still have, pressure changes and things like that, volume changes. Another thing to think about is a change from like 1 degree Celsius to 2 degrees Celsius. That's double multiplied by 2, but in terms of actual absolute temperature, it is not double. It's not even close. It's just a very small fractional increase. So we must convert temperature to Kelvin. Doubling 1 Kelvin to 2 Kelvin actually is a doubling, and doubling 100 Kelvin to 200 Kelvin is also a doubling. That's the kind of real proportions that we need in these questions with gases. Okay, so what do we know here? We know an initial volume, 88.5 milliliters, V1. We can use milliliters, that's fine. It's also centimeters cubed, but it doesn't really matter. What else? We've got initial temperature, 24.0 degrees C. We can't use that as it is. So plus 273.15 Kelvin, 297.15, but I need to keep my 1 decimal place when adding here, so I'll just write 0.1. Alright, what else do we know? T2, the final temperature at night, is 11.0 degrees C. Convert to Kelvin, plus 273. That's going to be 284.1, roughly. Again, I'm adding 273.15, but I can't have 2 decimal places due to significant figures rules, so I'm just writing 0.1 here. What's the new volume? That's our question. So, Charles' law. One thing I also want to say, you can write Charles' law in many different ways. V2 over V1. Oh, sorry, no. V2 over T2 equals V1 over T1. You could write that, that's true. But what if we multiply this whole thing, or multiply both sides, or not multiply, but take the reciprocal, take power to the minus 1, we will get T2 over V2 equals T1 over V1. This is also a version of Charles' law. And we could write, T1 over V1 on the left equals T2 over V2 on the right. You can change the positions of these things around to best suit what you're trying to find in the question. Okay, so here I would like to find V2. So I want this to be in the top left. V2 over T2 equals V1 over T1. This means V2, when I solve this, will be V1 multiplied by T2 over T1. So V1 is 88.5 milliliters. T2, 284.1 Kelvin. Divided by T1, 297.1 Kelvin. I'll bring this up here so you can put that in your calculator, but you should get 84.6 roughly. And we're canceling out kelvins here in the temperature. Milliliters should be our units. Okay. Does that make sense? We had 88.5 milliliters of a gas during the day. At nighttime, it cools down. The gas contracts to a slightly lower volume. It's not half, even though 11 is less than half of 24. It's just a small fraction smaller, and that's because we need to consider Kelvin temperatures instead. Okay, I think that's a reasonable answer to this question. Moving on. Next, Gay-Lussac's law. So this is very much similar. Pressure is directly proportional to temperature. So instead of volume this time, pressure is directly proportional with the condition that our gas is at constant volume and amount of gas. So we get P proportional to T, and we'll get a similar initial and final relationship here as well. P1 over T1 equals P2 over T2. And as I said on the previous slide, you can take the reciprocal of that. Sometimes it might be better for you to start with T1 over P1 equals T2 over P2. So these are the same. We will get a straight line graph again, direct proportionality through 0, 0. If we double temperature in Kelvin, we double pressure, assuming volume is held constant and number of moles or amount of gas is held constant. Also a very useful relationship. Let's see a practice question for this. So a round bottom boiling flask contains a gas at 27.0 degrees C and a pressure of 101 kilopascals. So just maybe some gas in a round bottom container in a laboratory at standard pressure. The flask is placed in a hot water bath then at 95.0 degrees C. What's the new pressure in the flask after being placed in the water bath? Okay, so here we have a round bottom glass flask. It'll have a probably lid on the top or stopper. That means the gas inside here cannot change volume. So we have some temperatures here. This must also be converted to Kelvin, but we're going to be using Gay-Lussac's law. So what do we have? We've got T1 is 27 degrees C. We need that in Kelvin, 300.1 roughly. We've got final temperature, it's going to 95 Celsius. We need that in Kelvin, plus 273.1, 368.1 Kelvin. So it's quite a big increase even in Kelvin. Then our pressure, initial pressure was 101 kilopascals. Question's asking us what's the final new pressure. We don't know that. Okay, so let me write this on the left. We'll have Gay-Lussac's law with what I'm looking for on the top left. Final pressure over, final temperature equals initial pressure over initial temperature. And I want to solve this for P2. So P1 T2 over T1. Then just put the numbers in. P1, 101 kilopascals. T2, 368.1 K. On the bottom, T1, 300.1 K. So our Kelvin units will cancel out. We will get an answer here in kilopascals, so put those numbers in the calculator. We should have about 3 significant figures here, so it's about 124 kilopascals. Again, does that make sense? We have gas in this round bottom boiling flask increasing its temperature by a significant amount. In a closed volume, the pressure must go up. So we get about an increase in 24 kilopascals, or 24,000 pascals. I'd say that makes sense. Good answer to this question. Okay. Moving on, there's one more law we need to consider, but it's one that we've considered previously today and in previous videos. This is Avogadro's law again. So volume is directly proportional to amount of gas, but a condition for this is, again, constant temperature and constant pressure. So if we have constant temperature and pressure, we will get the graph on the right here. As we increase amount of gas, as we're adding more and more particles, the volume must increase. That should make sense logically. So N is directly proportional to V. Amount of gas is proportional to its volume. And we can get the initial and final conditions out of this. V1 over N1 equals V2 over N2. Again, we'll usually get 3 unknowns and solve for the 4th one there. So I think I do have one example of that. Avogadro's law. I'm not too sure about this question. I made it up, but I think it's fine. It should work. A balloon contains 1.2 moles of gas, and it is 8.0 decimeters cubed at room temperature. That's its volume. And room temperature and pressure. Someone blows an extra 1.5 decimeters cubed into the balloon. It is then placed in a vacuum chamber until the gas inside reaches atmospheric pressure and temperature again. So the key here is I'm trying to indicate that we have a constant temperature and pressure, and we have volume being added to this balloon. So how many moles of gas are now in the balloon? So what should we have? Initial volume, 8.0 decimeter cubed. Initial number of moles, 1.2 mole. Final volume. So someone blows an extra 1.5 decimeters cubed. We're going to assume that 8.0 plus 1.5 is the volume even after it's placed in the vacuum chamber. So that is 9.5. And then how many moles are now in the balloon? How many particles, really? Moles are a representation of particles. We know we must have extra, but how much we need to calculate. So Avogadro's law, written to easily solve for N2, the new number of moles. So N2 over V2 equals N1 over V1, or N2 equals N1 multiplied by V2 over V1. Okay, put the numbers in. 1.2 mole multiplied by V2, 9.5 decimeter cubed, divided by V1, it was 8.0 at the beginning. So our decimeters cubed units will cancel out. We'll be left with a new number of moles. Put that in the calculator. You should get 1.425, but we need to have two significant figures max, so it's about 1.4 moles. So does that make sense? Somebody blows in extra volume into this container, this balloon. Yeah, it really should increase its moles slightly from 1.2 to 1.4. Sounds reasonable. Okay, so that's about it. The basic gas laws, these four ones, Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Really important to know these, and we will be putting these all together into one equation in the next video. But just some final points about this. Final notes. The shapes of the graphs we have viewed today will always be the same. So pressure versus volume, that hyperbola shape. Pressure versus 1 over volume, straight line through 0, 0. The others, temperature versus pressure, straight line through 0, 0. Volume versus temperature, straight line through 0, 0. And Avogadro's law, number of moles versus volume, straight line through 0, 0. But then my yellow point here, the slopes and potentially the positions of things like the hyperbola that we have viewed depend on the values of the things that are held constant. Okay, so I just want to go back and see an example of this. So here's Gay-Lussac's law, pressure versus temperature at constant volume. So I'm maybe analyzing a gas that's in a container of some volume. Volume doesn't change. But if I would change that volume to a new constant volume, maybe from 10 decimeters cubed to 20, a bigger container, and redo this experiment, I will get the same shape, this straight line, but it'll have a different slope, okay? The slope of this depends on what I'm holding constant, which is the number of particles and the volume. Similar things could be said for these other graphs. Charles' law, if I change my constant pressure to something else and redo the experiment, I'll get the same shape, but the slope will be different. If I change my temperature of the gas for Boyle's law, the hyperbola on the right may get different slope, and it will also move diagonally, either closer to the origin 0, 0 or farther away, while maintaining basically the same shape. Okay, so that's just something important to keep in mind when considering all of these graphs. All right, then that's all for today. I think that's a good place to stop, almost 48 minutes. So hopefully you learned some things about ideal gases, and we'll continue this discussion in my next video. Thank you for watching. Best of luck. See you next time.